we're going to talk to you about reflecting and refracting telescopes. Talk about how they work. This is Hawaii. Yeah, on top of a mountain. You get away from the city. Don't have to worry about light pollution. You try to get as high up in the atmosphere as possible, so you don't have to worry about the air destroying the images you see, like atmospheric blurring. So we use a telescope to gather light from objects in the universe to see images. We'll talk about the history, lenses, reflecting, and refracting telescopes. So Hans Lippershey invented the first refractor telescope. That's like your standard telescope, long tube eyepiece lens. Galileo used it, and he started to mix convex and concave lenses. We remember that concave. Remember the big C was cave, thin in the middle, convex thicker in the middle. Kepler improved the design using two convex lenses. It made the image upside down, but what you're able to do is get a larger image coming in, and we'll talk about how that works. Like it was like your eye. When objects are really far away, it does not take up enough space on your eye. You can't see it properly, and so you bend the light with lenses and bring the image closer to your eye, make it smaller. So the lens in your eye, and we'll talk about the structure of the eye later, but the light bends, it goes through a different medium, and they intersect with the glass, and they focus. The image is focused by your retina. And that's why sometimes when you have a lot of light around the retina, your pupil is that little black spot in the middle of your eye. When you have a lot of light, your pupil is really small to not let too much light in. And when it's dark, your pupil is really large to let a lot of light in so you can see better. So if you have a bigger eye, you collect more light from the object. So like when you do reflector telescopes with large mirrors, the larger the mirror, the better the objects. The easier it is to see, the stronger the magnification is. So you have the objective lens, the refractor, or the primary mirror. Then you have your eyepiece or the objective, just like the microscope. The objective lens and refractors are primary mirror and reflectors. Get your light, they bring to a point of focus. Remember your focal length, focal point. And it helps you to take up a large portion of your retina so you can see things. So here's your diagram of a simple microscope. They enter through from the left, they pass through the objective lens, they focus on the focal plane, and then the focal length of the objective is f, and the focal length of the eyepiece is f, small f. When you combine the lenses together, you have a telescope. You want a lot of light, and you bring it so you can see it. Two general properties: how well it collects the light, which is the aperture, like a camera. It's the hole you see through things. When you hear the word aperture, it means like hole. And how much you can magnify the image. So the aperture is your how big your diameter of the lens or mirror is, and it's what you use to gather the light. The larger the aperture, the more light the telescope has, and the brighter the final image. You have to watch out for resolution. Resolution is your ability to separate things you see in an image. If you have poor resolution, everything blurs together. That's why having telescopes inside the atmosphere is difficult because of the interference from the air. When you start talking about incredible distances, these things make a difference. The magnification depends on the combination of lenses used. So here's your eyepieces. Note the image is upside down. Sometimes they use computers and adaptive optics to correct for this atmospheric blurring and the effect of the images being inverted or upside down. So you produce and allow you to change the telescope's magnification, you get a sharper image, you get eye relief, and it determines the telescope field of view. How much in the sky can you see, the true field, and how much of the sky in degrees is seen edge to edge to the eyepiece alone. So you can change your eyepieces so you can see more of the sky at one time. You use filters, and this helps you moderate the wavelength of light that comes through. And you have light pollution filters and color filters to enhance it. You have to watch out for, like being in the sea, you have a lot of light around you. It makes images in the sky seem darker. And you want contrasted features of the moon and planet. And you also want to have a filter if you want to view the sun, because you can't just look at the sun. There are two types. You have the refractor and you have the reflector. One uses glass, and one uses mirrors. The refractors are a type of telescope we always see. It's a long tube. You have two lenses, and eyepiece and objective lens. And here it is. You have your eye, you have the eyepiece. It brings the image from the focus, magnifies to the size of your eye pupil. There's incoming light, the objective lens, and the simplest one, okay? The refracting telescopes are not used for astronomical research because they're large and have heavy lenses. Lenses are very expensive to make, because the larger the lens is, the more you can see. So here it is, the common, but the aperture, the final lens here, is really expensive to make. You get really nice images though. You have your small one and you have your 40-inch refractor. But look at the size of the thing, right? It creates a serious issue in terms of space also. Then you have the reflecting telescope. Newton developed the first one. There's chromatic aberration, and what that means, chromatic means color, and aberration means like blurring or problems. An aberration is like there's an issue, okay? And instead of using a lens together, like he used a curved metal mirror to collect the light reflected to a focus. And because the mirror reflects the light back into the tube, he can use a small flat mirror, a secondary mirror. And so you can see things, and we'll see it in the diagram. John Hadley developed a design that used a parabolic mirror. And then Newton this was a very popular design, and he made improvements upon this, and we'll talk about that also. Parabolic mirrors are like parabolas. They're curved surfaces, convex, concave, etc. So here's your telescope. You have a primary mirror that bounces off another mirror, secondary mirror, and you can see it right here. And this will bend it. You have the Cassegrain focus. Cassegrain means the light bends several times. So you have a primary mirror, and it binds off a secondary mirror, and then you see it at the focus here. So you don't need as long a distance, a focal length, because it's bending within the mirror. So instead of having to be like a 40-foot mirror, you can make it a 20-foot mirror because it bends twice. Here's your Newtonian focus, pretty normal. One mirror, and then another mirror to focus it. And we'll exclude the quad focus because it's just redundant. It's about the same thing. If you want bonus, you can do a little research on the quad focus and send me a little article or web link, and I'll share it with the class. So here's the Newtonian reflector. The primary mirror bounces off a secondary mirror to your eyepiece. And you have smaller ones, a 6-inch amateur. Low cost, simple, good image quality. There might be an obstruction in the center, but that's okay. The Cassegrain Reflector, and you have a large focal length in a small package because it reflects upon itself. So you get good images, and it's designed for large microscopes. Once again, it reflects. You have the image come in and go back out and come back in again. And what that does is it doubles your focal length in a smaller space because it travels 2 times. Then you have the Schmidt's Cassegrain, where you have a collector. You have a large number in a smaller package, and you have better spherical aberration control. Spherical aberration is like, when you use the fish eye effect on your iPhone or super wide on your GoPro, it's a curve at the end of the edges, on the edges. That's your spherical aberration. Chromatic aberration is you have the light coming in, the wavelengths spread out, and so colors become skewed, screwed up, and it looks like a rainbow. So they fix that by modifying with a second lens so that the focal point for all colors is in one point. Spherical aberration is it doesn't focus. It's not focusing in the proper place. And all you do is use a parabolic mirror where you have one focal point for all the light rays. Remember, not everything is visible. You have they don't all use modern visible light to collect images. Sometimes they use radio telescopes. They use X-ray and infrared because you can see things farther, and you don't have to worry. You want to look at specific things in the sky. So if you're looking for suns instead of planets, infrared is really good because you see the heat. Here's some famous telescope. I think they're all located in Hawaii. Whoa. And here's a radio telescope. We'll talk about that later.